Okay, so let's begin now. The next topic is singular value decomposition. And if you have followed last lecture on spectral decomposition, then you would notice the similarity. In fact, SVD, singular value decomposition, is a generalization of spectral decomposition. Spectral decomposition holds for square matrices. SVD can be applied to any matrix. Okay, so we'll do full SVD and reduced SVD. Then we'll look at the geometric interpretation of SVD, and then some properties of SVD. That will be today's lecture, and it's probably going to be shorter than usual. But at the end, I'll also uh, show you a little Matlab demo of SVD. Okay, so this is a M by N matrix, A. And we can assume that M is greater than or equal to N, so that A is a tall matrix. So the SVD, the full SVD of A is equal to U and then this matrix sigma 0 B transpose, which is equal to U1, U2 until UM. So you have this matrix with M columns. And what's the dimensionality of each column? U. It's also M, right? Because A is a M by N matrix. So this has to be, this has to have M rows, which means that each of these U's, columns U, is of dimensionality M, M as in misery. We're lucky we have one state, Nebraska, which starts with an N, and one Missouri, which starts with an M, bordering Kansas. Anyways, so this is how this block matrix sigma 0 looks like. So here we have sigma is this part, this upper block, sigma of this matrix is a diagonal matrix, and its diagonal elements are sigma 1, sigma 2 until sigma n. This is a M as in Missouri times N as in Nebraska matrix, M by N. So it's of the same size as A. Okay, and so this is a diagonal matrix, and then below that you have a block of all zeros. And then V transpose, if the columns of V are V, this matrix V are V1, V2 until Vn, then V transpose has its rows V1 transpose, V2 transpose until Vn transpose. Okay, so this V transpose has n rows, and how many columns? This actually is a square matrix, so it's a n by n matrix. Okay, so this is the full SVD, and this is what it looks like. Okay, and here U is a M by M unitary matrix, and V is a N by N unitary matrix. I have V transpose here. Okay, and so V transpose also is an N by N unitary matrix. Okay, and since they're both unitary matrices, U transpose U equals UU transpose equals I, the identity matrix, and likewise V transpose V equals VV transpose equals I, the identity matrix. This is a identity matrix of size M, and this is an identity matrix of size N. Always keep track of these sizes. Anyways, and this matrix sigma is a M by N matrix, so it's of the same size as A, and these diagonal elements of sigma, lowercase sigma 1, lowercase sigma 2, lowercase sigma 3, they are called the singular values of the matrix A. And they're always positive. And they are arranged in this manner. Sigma 1 is the largest one. They're all positive, non-negative at least. Sigma 1, and then sigma 2, sigma 3, until sigma n is the smallest one. Okay? Every matrix has one and only one SVD. So the SVD of a matrix is unique, as long as these are arranged in proper format. And of course, you can invert U's and V's, just like in eigenvectors. These U's and V's are also just directions. Okay, so this is the full singular value decomposition of the matrix, and it's a unique decomposition. Okay, the matrix can be expressed as a summation. A equals summation sigma I ui vi transpose. How do we show that? Okay, so this is the full SVD. And so expressing U in terms of its columns, U1, U2 until UM, and then this is sigma, and this is V transpose. Now I proceed to do the multiplication. If I multiply the second matrix here with this third matrix here, what do I get? Sigma 1, B1 transpose, and everything else gets multiplied by zeros, right? So the first row of the product of the second and the third matrices would be sigma 1, B1 transpose. The second one would be, so here you would have 0, then sigma 2, then a bunch of zeros. So 0 gets multiplied with V1 transpose, 0. Sigma 2 would get multiplied with V2 transpose. So you would have sigma 2, V2 transpose. The third row would be sigma 3, V3 transpose. And the nth row would be, so sigma n, Vn transpose. And then beneath that, you'll have a bunch of all zeros. So all zeros will be getting multiplied with these vectors here. And so you'll end up with a bunch of zeros. So this is what I get when I multiply the second and the third matrices. Okay, and now this is my U. Here I have explicitly expressed U in this form. So U1 through UN, you know, this has m columns, mn as in misery, but since we assume that n is smaller than m, so I have U1, U2 until UN here, and then UN plus 1 until UM. I'm trying to visualize this matrix U in terms of the first n columns and the remaining columns here. Okay, so now let me proceed with the multiplication. Now I multiply this with this. What do I get? Sigma 1 is a scale, U1, sigma 1, V1 transpose, correct? Plus U2, sigma 2, V2 transpose, plus U3, sigma 3, V3 transpose, plus dot, 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 until UN, sigma n, Vn transpose. And then all these column vectors, UN plus 1 through UM, will be multiplied by all zeros. Okay, so I'll end up with sigma 1, sigma 2, these are all scalars, so I can bring them to the left of each factor. Sigma 1, U1, V1 transpose, plus sigma 2, U2, V2 transpose, plus sigma 3, U3, V3 transpose, until sigma n, UN, Vn transpose, and then a bunch of zeros. Okay, And so this is what I get, which basically shows that A equals summation sigma I ui vi transpose until n, not m. Remember, this is the smaller of the two dimensions. Okay, n is the smaller of the two dimensions because I assume that A is a tall matrix. Okay, so this is how I can express A in terms of a summation of rank 1 matrices. Each UIVI transpose is a rank 1 matrix, and I'll just show it to you in Matlab after this lecture. Okay, so reduced SVD. So this is what I have. Now these UN plus 1 through UM, these columns of this U here were getting multiplied with a bunch of zeros, correct? So that's why, in fact, the summation ends at n. We just discard the remaining terms, which are zeros, okay? And so what happens? We can just drop these. Okay, and so this is what we got. And when we multiply this with this, and then this, if I can just ignore these, this block here and this block here, I can express this as this here. So the first factor, all I did was take the first n columns of U. And I just took the diagonal elements here, and then this remains the same. This is V1 transpose until Vn transpose. Okay, now what happens? This has n columns. All these are m-dimensional vectors, m as in misery, so m by n. Okay, and this is now a square matrix, a square diagonal matrix, sigma, and this still remains the same. This is the reduced SVD. A equals U sigma V transpose. Remember here, U is no longer a square matrix. Okay, so this is the SVD of A. And this is what it looks like. U is a m by n matrix. It's of the same size as A. And V is the usual, it's the same as a full SVD, and it will be a unitary matrix. But U can no longer be a unitary matrix. Why? Because it's not even a square matrix. So U transpose U will be equal to I. Because when we began with U, the original U, all these columns were unit vectors and mutually orthogonal to one another. That's why it was a unitary matrix. And now, since the columns are still mutually orthogonal to one another, we would have U transpose U equals I. But U transpose would not be equal to the identity matrix. It wouldn't be of full rank n to begin with. And since V we have preserved from the full SVD, it still is a unitary matrix, so that V transpose V equals VV transpose equals I. Any questions so far?
No.
Okay. Now, if A was a wide matrix with more columns than rows, then you can easily visualize what the SVD, the reduced SVD and the full SVD would look like. I would leave that as a exercise, but we can of course demo it in Matlab. Okay, so this is the reduced SVD. And always note that the singular values, these are the singular values, the diagonal elements of sigma, they are always greater than equal to 0, and they are sorted in descending, I don't know which one is descending, but the first one is the largest. Sigma 1 is greater than equal to sigma 2 until sigma n. Now, what would be the highest rank of A? If it's an m by n matrix, the rank would be the lower of the two, right? N. So if this were full rank, n, full column rank, in that case, all these would be strictly greater than 0. Okay, and so it depends on the rank. Suppose this is a 10 by 5 matrix of rank 3, then only the first 3 singular values would be greater than 0, and then the other 2 singular values would be zeros. So this is a comparison between the full SVD and the reduced SVD. All I did was, this is the full SVD. I just chopped off the rightmost columns of U, and I also dropped the bottommost block, which were all zeros, unnecessary, in this, and so I was left with a reduced SVD. Now, let's, before we go into the geometric interpretation of SVD, let's just quickly remember what the geometric interpretation of the spectral decomposition was. Okay, if you remember, let's say we have this matrix A here, a square matrix now, and its eigenvectors. This is, let's say, a symmetric matrix. Okay, if this is a symmetric square matrix, then here are the eigenvectors V1, V2, V3. They are all mutually orthogonal to one another, right? Okay, and so if V1 is here, what would AV1 be? Lambda 1 V1, right? So if I take any eigenvector, Vi, AVI would be equal to lambda IVI. That's the definition of eigenvalues and eigenvectors. But now what happens? So if you project the whole unit circle, let's say this is a unit circle, this shaded region here, excuse me, not a unit circle, but a unit sphere. This is a three-dimensional hyperellipsoid, and it has, since it's three-dimensional, it will have three axes. The major axes, the largest axis would be along V1, and the length of the I don't know what we call the axis, the whole thing from one end to the other end, or the center of the ellipsoid to one end. I don't know officially what an axis is, but anyway, the length of this vector along the axis from the origin, which is the center of the hyperellipsoid, along V1, this is of length lambda 1. And V2, this is lambda 2 V2. So this axis here of this hyperellipsoid has a length lambda 2. That's from 0 to the surface. And likewise, lambda 3 V3. So this V1 is the direction of maximum stretching, right? And V2 is the direction of next to maximum stretching, or in other words, it's the direction of maximum stretching that's orthogonal to V1, and then V3. Okay, so these give us the direction of stretching, and these eigenvalues will tell us how much it will stretch or compress. Okay, that's for spectral decomposition. And remember, V1, lambda 1 V1. V2, here lambda 2 V2. So the directions are the same. This red arrow here, you take the projection, y equals ax. If this is the space of vectors x, unit vectors x, let's say, are all confined to this sphere, then, and this is the space of projections, y equals ax, then you see, as long as we take the direction of an eigenvector, the directions won't change when you do the transformation, y equals ax. Okay, otherwise the directions would change, by the way. Any questions so far?
No.
Okay, so now back to singular value decomposition. This is the geometric interpretation as follows. A is our m by n matrix. Okay, and now we are mapping an n-dimensional vector, so linear transformation, to an m-dimensional vector. Okay, so x belongs to R n and y belongs to R to the m. So this is full SVD. The V's are orthonormal. Okay. So why are they orthonormal? Because V is a unitary matrix. So all the VI's are unit vectors and they're mutually orthogonal to one another, which is the same thing as saying that the VI's are orthonormal to one another. So in this n dimensions, okay, this is n dimensions, these VI's can act as coordinates. They're unit vectors and they're all mutually orthogonal to one another. Now, turning our attention to this, okay, so now any x, we'll turn our attention to u later. So any x can be represented as a linear combination of these coordinates, v1 until vn. Okay, and the coefficients are alpha 1 through alpha n. Therefore, x can be represented in this form: summation of alpha I vi. Okay. Now, suppose we make x a unit vector, L2 norm. What can we say about the alphas? Alpha 1 square plus alpha 2 square until alpha n square would be equal to 1, because this would be equal to the square of this L2 norm. Correct? Okay. Now, let's turn our attention to this other matrix, U. U is a unitary matrix, which implies that the columns of U are also orthonormal, just like those of these. So these UIs also can act as basis vectors or coordinates in this larger n-dimensional space, correct? Now, any questions so far? Okay. So A equals summation sigma I ui vi transpose. We saw this. Implies AVI equals sigma I ui. Why so? Well, because if you pre-multiply both sides with VI, okay, this left side becomes AVI. Now what happens to the right side? You have V, well, let's say I let's call this J here. Instead of I, let this be J. So we would have J this is J and this would be J. Oops. Okay, and then when I pre-multiply both sides with, I'll undo everything. So what would happen if I not pre-multiply, post-multiply? Did I say pre-multiply? Post-multiply. Both sides with VI. And here, this. Now, what would happen to Vj transpose Vi? Since Vi and Vj are orthogonal to one another, if j is not equal to I, what would happen to this? It would be 0, correct?
Yes.
And if when j equals I, what would happen to this? This would be equal to 1, right? So in other words, I would all terms except the ith term of the summation will become equal to 0. And the ith term will be equal to sigma j vj. I'm just undoing everything. Okay. Which means that AVI equals sigma I ui. Okay. Remember this. This is important actually. AVI equals sigma I ui. Now x was my unit vector, which was a linear combination of the basis vectors v1 through vn in my lower dimensional Euclidean space. Okay. This is n dimensions. Okay, and so this is summation alpha I pi. Y equals ax, which is equal to, I just pre-multiply both sides with ax to get y. So this becomes, y becomes equal to alpha 1 av1 plus alpha 2 av2 until alpha n avn. But av1 equals sigma 1 u1, right? Therefore, av1 I replace with sigma 1 u1. Likewise, av2 I replace with sigma 2 v2, sigma 2 v2, and all the way until the last term here, avn is sigma n un. So you have alpha 1 sigma 1 u1, alpha plus alpha 2 v2 u2 plus until alpha n sigma n un. Okay, so now this y is being expressed in terms of u's, these u's. X was being expressed in terms of v1 through v and v's. And y, notice the difference, is being expressed in terms of u's. What is the L2 norm of y? Alpha 1 sigma 1 squared plus alpha 2 sigma 2 squared until plus alpha n sigma n squared. You take the square root of that to get the L2 norm, or L2 norm squared y transpose y is equal to this. Agreed?
Yes.
And alpha 1, alpha 2, or here, actually, I could have taken the squaring, square operation inside the inside. So this would have been alpha 1 square sigma 1 plus alpha 2 square sigma, so, excuse me, alpha 1 square sigma 1 square plus alpha 2 square sigma 2 square and so on. Okay. What I meant to say was sigma 1, sigma 2, and sigma n, these are all positive numbers, non-negative. Alphas can be plus or minus. So this is my x, L2 norm of x squared, or the length of x squared. It's 1. And this is the length of y squared. Okay, so this is what is happening. This is, notice that I expressed y in terms of the u's. Okay, so I have two different spaces here. One is this on the left. I have a smaller n-dimensional space, n as in Nebraska. On this side, right side, I have an m-dimensional space. What's the m? M is, it comes from these. Okay, so I have m as in Missouri, m number of coordinates, right? Basis vectors, U's in my m dimensions. And y is an m-dimensional vector. Sorry about this. So y is an m-dimensional vector, right? And so I'm using these u's here, u1 through um will serve as the basis. It just so happens that y can be simplified, so only these terms would be relevant in this y. We are dropping sigma n plus 1 until sigma m. Okay, and now what's happening here? I want to maximize y with x being a unit vector. What do I do? What would be the direction? Now I have to choose my alphas, right, to maximize y. I have to choose my alphas in such a manner that this is maximized while this is maximized, but alpha 1 squared plus alpha 2 squared until alpha n squared is equal to 1. So what do I do? Are you guys with me? Or
Yeah.
so what do I do then? If I just want to maximize, I want to pick a direction. Okay, I want to pick an x.
You could pick
A
the
unit
direction
vector
of
x.
u1.
What's that?
You could pick the direction of u1 and assume some
Not
value.
u1, v1. From here,
Sorry,
x
alpha.
will be v1, right? See, x is in
Yes.
this Euclidean space, which is n dimensions, n as in Nebraska. This is y, which is m as in Missouri, dimensional Euclidean space. So what I do here is, since sigma 1 is the largest of my singular values, right? So I simply let alpha 1 be equal to 1. And therefore, all the other alphas would be equal to 0, correct? And so y would be, x would be, so alpha 1 is 1, and all the other alphas would be equal to 0. So I would pick v1. You said u1, and basically your intuition was 100% right. It's just that this is v1. I pick x equals v1, and that would give me, what would y1 be? Or sorry, when x is v1, okay, so alpha 1 is equal to 1. And all the other alphas are equal to 0. So y would be equal to sigma 1 u1, correct? So y here would be equal to sigma 1 U1. So if I pick X equals V1, then I would get the maximum amount of stretching. This is the projection of this unit sphere, this three-dimensional or m-dimensional hyperellipsoid. And this is the direction of the maximum amount of stretching you would get. And what is the amount of stretching? If you take a unit vector and then here x, then the length of y would be sigma 1. Okay, but unlike in spectral decomposition, the directions are changing, right? This is V1 and this is sigma 1 V1. This geometric interpretation is basically the same, very similar to that of spectral decomposition, but in spectral decomposition, the directions were not changing. We were confining our attention to square symmetric matrices there, and so the directions couldn't change. V1, and here you get sigma 1, lambda 1 V1, right? But now the directions are changing, and the amount of stretching is determined by the singular values. And now if I were to pick a direction, my problem now is to pick a direction that's orthogonal to V1. I have to pick X, which is orthogonal to V1, that would give me the maximum value for Y, the length of Y. What should I then do? Since I'm confined to a hyperplane that's orthogonal to V1, it means I have to make alpha 1 equals 0. If with alpha 1 equals 0, how do I maximize this? By setting alpha 2 equals 1 and all the remaining alphas equal to 0. Correct? So what would happen then is, okay, so just going through the slide. So X equals V1 is the original one. No constraint that it should be orthogonal. So X can be any unit vector. X equals V1, then length of AX is sigma 1. Sigma 1 equals maximum of L2 norm of AX, where X is a unit vector, and V1 is the argmax. Okay, and AX equals U1. We all saw this just now. Now, if I want to pick another direction that's orthogonal to V1, then I must pick V2, correct? This doesn't show it, but V1 and V2 are orthogonal to one another. Actually, V1, V2, V3, all the V's are orthogonal, and likewise, all the U's are orthogonal to one another here. So the next highest stretching direction is along V2 here. So if I pick X equals V2, I would get Y equals sigma 2 U2. So sigma 2 equals max of X unit vector X orthogonal to V1 of L2 norm of AX. And V2 is the argmax. And I proceed in a similar manner. So AX equals V2. Now, when AX equals U2, when X equals V2. Okay? So this is the geometric interpretation of the singular value decomposition. Okay. Any questions? If you were paying attention to my last demo, then you would know, you would have a clear picture of this one. It's there in the video anyway, so you can always have a look later if you forgot. Okay, now the columns of V are the eigenvectors of A transpose A. Okay. What's V? V is obtained from the SVD. This SVD. A equals U sigma V transpose. So the columns are V are the eigenvectors of A transpose A. And suppose we have the SVD of a square matrix A. Actually, why should this be square? A transpose A. So we have a tall matrix A, M by N matrix A. Okay, then A equals U sigma V transpose. So A transpose A. Why I'm choosing a tall matrix is because then this would be N by N matrix. If this were N as in misery by N matrix A, then A transpose A would be N by N. And so this is the reduced SVD. So A equals U sigma V transpose. What is A transpose? Equals the transpose of this, which is I reverse the order of these factors. So V transpose transpose, which is V sigma transpose U transpose. Okay. And what is A transpose A? V, this is A transpose, V sigma transpose U, and then this is A U sigma V transpose. This is not UU transpose, it's a typo here. Sorry, this is UU transpose. It's U transpose, not UU transpose. Okay. U transpose U. What's U transpose U? I, the identity matrix, because U is unitary. So I'm left with sigma V transpose sigma V transpose. Okay. Would it be V transpose or transpose? What would this be? Transpose, transpose. Oops, there's a small mistake in my. No, that's correct. So this would A transpose A would be equal to V sigma square V transpose. Correct?
Yeah.
Sorry about this typo. And we are looking at a tall matrix M by N. Any questions? Sorry about this little digression. But anyways, this is A transpose A. Now, what is sigma? Sigma is a diagonal matrix, correct? So what are the entries of sigma square? Sigma square also would be a diagonal matrix whose diagonal elements would be the squares of the singular values. Sigma 1 square, sigma 2 square, and so on. Right? So this is also a diagonal matrix. Okay. Now compare with the spectral decomposition of A transpose A. A transpose A is a N as in Nebraska, N by N square matrix, correct? And it's also symmetric. A transpose A would always be symmetric. So compare that with the spectral decomposition. What does the spectral decomposition of A transpose A, what would that look like? The spectral decomposition of the matrix would be, from the spectral decomposition theorem, it would be of the form V lambda V transpose, right? V lambda V transpose would be the spectral decomposition or eigendecomposition of this square matrix. And so some of the V, some of the lambda, but if you compare with this, the V's are the same. So this is basically the spectral decomposition of A transpose A. This is the diagonal matrix. This is the uppercase lambda of the spectral decomposition. Whence lambda 1 would be sigma 1 square, lambda 2 would be sigma 2 square, and so on. Okay. Anyways, so now the columns of V are the eigenvectors of A transpose A. The columns of U are the eigenvectors of A transpose. Now here I'm taking a larger matrix. If I pick M by N matrix with M as in Missouri being more than N as in Nebraska, a tall matrix A, then A transpose would be a bigger size matrix, M as in Missouri times M as in Missouri, M by M. And so the columns of U are the eigenvectors of A transpose, and I proceed exactly the same direction. A is U sigma V transpose, A transpose is V sigma transpose U transpose, and so A transpose is equal to U sigma square V. So the columns of this U are the eigenvectors of A transpose. And the singular values of A are the square roots of the absolute values of the eigenvalues of A transpose A or A transpose. Okay. Sigma I is square root of this. And we saw this already. A transpose A was here you had sigma square, here you had sigma square 2. Okay. So before the review, I guess you would like a little demo. Do you guys seem a little lost today? Is that am I correct? Or you have...
I had a question.
Oh, sure.
Can there be a situation where the singular values are complex, or are they always real? And
no, they're always real, as long as A is has real elements.
Okay. Okay. If the matrix has complex elements, then the singular values might be complex.
Even then they will be real, because A transpose A will be a Hermitian matrix, okay. Right? So even then they will be real.
Okay. Okay.
So let's take A equals rand, let's say 6,5 plus I star rand 6,5. Okay, where I is square root of -1. So U S V equals SVD of A. So these are the singular values.
Yeah, they are all real and positive. Yeah.
Okay, and you also see that they are arranged, they're all sorted. This is sigma 1, 4.4654, 1.2580, 1.0790, and so on, correct? Okay, so even if I took a complex matrix, it still has real singular values. But these, of course, U and V will be different. They will be complex. Okay, now this is my USV, right? So U star, S is my sigma star, V transpose, this would be equal to A, right? And compare it with A, I'm getting exactly the same, right? So U sigma V transpose is equal to A. Okay, let me take a oops. I just rounded off, and star A, rounded it off so that you can, oh no. So this is, you can visualize this better now. Okay, that's why you rounded it off. Okay, now USV equals SVD of A. Okay, is this full SVD or reduced SVD?
This is full SVD.
This is the full SVD, right? Let's do another one. Maybe I'll take 7 by 4. Okay, and then U, so this is a square matrix, U. And U is similar, right? U star U transpose should give me the identity matrix. This is the identity matrix. And V's or U transpose star U should also be the identity matrix, correct? Because U is a unitary matrix. This is my V. Now V is also unitary. So V star V transpose is the identity matrix. You can see that this is an identity matrix, right? All these were identity matrix. These are all, due to numerical reasons, I get all these negative signs, but these are all numerically very small, negligible, all these zeros. Only the diagonal elements are 1. Okay, so this is V, and now what is S? So S is the diagonal matrix formed out of the singular values of A. Okay, now, so let me just replace S with diag S. So I just take the diagonal element. So these are my singular values. Now, let me do L equals lambda. I want the eigenvalues of A transpose. I's A star A transpose. Okay. Now, what's the size of A star A transpose? My matrix A is, what's the size of A? I can look up here. A is 7 by 4, right? So what would be the size of A transpose?
7 by 7.
7 by 7. But what would be the rank of A transpose?
4.
It would still be 4. In other words, it would have only 4 non-zero eigen values. So let's take a look. This is A. Oh, I have to take the square root. Never mind. The square roots of the eigenvalues of A transpose. Okay, so I'll take L equals RT and compare it with S. They're the same, right? ignoring these two zeros, okay, I have, this is the square root of the eigenvalues of this AA transpose are nothing but the singular values. 10.4967, 10.4967, 7.6069, 7.6069 until this one, right? And likewise, if I take for L, eigenvalues of A transpose star A, then I take the square root of that, I get these, which are the same as the similar values. Okay.
Yes, Dr. Lass.
Hmm?
Yes, it's clear.
Now, do you want to see any this stretching thing, or are you good with that? Because I did a pretty good demo last time. I don't want to write any plot commands, but I can demo you. Let's do a little demo of that too. So now let me confine myself to a smaller matrix. Let's say size 3 by 2. This is A. Okay, actually, maybe I don't do this rounding up. This is my A. Okay. A. And now, let me do the SVD. So I get USB. So X, I take any X. So what are the basis vectors in my three-dimensional vector space? The elements of U, sorry, the columns of U, right? So V1 equals U1 equals U all comma 1. U2 equals U all comma 2. U3 equals U all comma 3. Okay. And so these are my basis vectors. And then I choose my alpha to be, what do we want it to be? 0.6. I'm just using vector. So alpha is a vector. Let's say negative 0.6. Like confine ourselves to 4, negative 2, and 3. So X is equal to this 4 times RB1 plus correct? U1, U3, sorry. U2 and this is U1. What's alpha 1, alpha, oh, 3. So this is my X. What's the length of X? It's actually square root of this, right? 4 square plus negative 2 square plus 3 square, right? So length of x would be the same thing as norm of alpha. Agree? Do you guys see this? But x is also norm of x would give you the same value, 5.3852. Okay, so the L2 norm of x is alpha 1 square plus alpha 2 square plus alpha 3 square. Now let's take y equals a star x. A is, what's the size of A? Oh, you know, I made a mistake here. Sorry about this. What are the basis vectors of for this x? They're the v's, and the basis vectors of y are the u's. Okay, so never mind this. Going back here, what I will do is just a quick fix. So alpha is equal to, let's adjust this. Okay, and x is equal to, oh, I need v's too. V1, what's v? It's 2 by 2, right? It's 2 by 2, yeah. So v1 equals v all comma 1, v2 equals v all comma 3. Okay, 2. B is a 2 by 2. So the basis vectors for x are this v1 and v2. The basis vectors for y would be u1, u2, and u3. Okay, so x equals this. This is my x. Okay, now norm of alpha is equal to this 4.4721, and norm of x would be equal to that. So the length of x is now square root of alpha 1 square plus alpha 2 square. X is 2-dimensional. Y equals ax would be 3 dimensions. Agreed? So now, what are the directions? What are the components of y along u1, u2, and u3? Y star u1, y transpose star u1 is 2.1921, right? So if I project y in the direction of u1, u1 is already a unit vector, I get this. Okay, so in other words, let's do this. One plus, this is the projection of y along u1 times the vector u1. So what I'm doing is I'm trying to express y in terms of U1, as a linear combination of U1, U2, and U3 plus, are you guys following this?
Yes.
Okay, okay, so now what should I get? And is this equal to Y? Yes. Correct? Okay, now what are the singular values of S, of A? Okay, what, so now, how should I explain this? What is this, by the way? Yeah, this is 0. Basically, it's a linear combination of U1 and U2. Okay, so what's the direction of maximum stretching? Okay, another way of, let me do it this way. So this should be equal to, this coefficient should be equal to sigma 1 alpha 1, correct? And S1 star Al 1, what, same thing, right?
Yes.
And let's look at this, the component of Y along U2, and this should be this. Oops.
Should be S2, 2.
What went wrong?
It should be S2, 2 multiplied by alpha 2.
All right. So, sorry. Correct? And it's the same as this one. Okay, so basically what I demoed here is this. Going back to the slides, the components of Y, see, are you looking at the slide now?
Yes.
So X was this alpha 1 V1 plus alpha 2 V2 until alpha and Vn. So the components of Y along U1, U2, and U3 were this, right? Y transpose U1 was alpha 1 sigma 1. Y transpose U2 was alpha 2 sigma 2. Right? That's what I wanted to demo. Now, one last thing. Are we guys completely clear with this?
Yes.
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 So now I wanted to show you this. I'll take X equals ran let's say 4 comma, actually I'll do this. X equals 5 negative 2. Even better, I'll do this. X equals 1 through 4 and X equals X transpose. So this is my X. 1, 2, 3, 4. Okay. Y, I'll take another, make another vector Y, again 4 dimensions. 10, 100, 1000. So this is my y. Okay. Now, x star y transpose would be a 4 by 4 matrix. Agreed?
Yes.
But what would be the rank of this? Let's not look at A, but rank of A would be, so I'm taking a vector, okay, x, and take another vector, y. So xy transpose. Okay, so xy transpose, it's a matrix. What's the size of the matrix? It's a 4 by 4 matrix. But what's the rank of A? It'll be 1. And you can clearly see why. If you look at each row, the second row is 2 times the first row. The third row is 3 times the first row. That's why I picked x equals 1, 2, 3, 4. And the last row is 4 times the first row, right? So how many independent rows do you have? Just 1. Column, if you look at the columns, 1, 2, 3, 4, the second column is 10 times the first column, the third column is 100 times the first column, and the last fourth column is 1,000 times, right? So how many independent columns do you have?
1.
1.
That's why the rank of A is 1. Okay. So any questions?
No.
No.
Okay, so we can conclude today's lecture 2 and see you next week.
Okay. Thank you, Dr. Tan.
Thank you.
Thank you.